Okay, let's get started today's seminar. Today's seminar speaker is Professor Mikhail Shaposhnikov, and he will talk about Einstein-Cartan gravity. So please start.
Okay. Hello, everybody. I'm glad to give this seminar, being virtually in Korea. Okay, so what I'm gonna talk here is about Einstein-Cartan gravity, and I will try to convince you that this is a very interesting theory, which can give us some hints about electroweak symmetry breaking, about inflation, and also about dark matter. So the works which I'm going to present here, so there are basically 5 papers which were written this year. So the first 2 papers are by Andrei Shkerin and Sebastian Zell. So here I will talk about electroweak symmetry breaking and Palatini Higgs inflation. And then there are 3 other papers where Inar Timirazov joined us. And here I will talk about Einstein-Cartan gravity, Higgs inflation, and dark matter. So there are 2 papers. This is just 1-hour talk, if I understand correctly. So many things will be squeezed quite considerably. Okay, so what I'm going to do, I will first remind you what are these different versions of gravity. What is gravity metric formalism and Palatini? What is Palatini gravity? What is Einstein-Cartan gravity? Then we will see that there are a couple of new terms which appear in Einstein-Cartan gravities in comparison with metric gravity. They're called Hall's term and Nieh-Yan invariant. Then I will discuss bosonic action in Einstein-Cartan gravity with the Higgs field, and this is the place where different incarnations of gravity start to be different from each other. Then I will talk about non-perturbative generation of electroweak scale, about inflation, and about dark matter. Okay, so what are these different gravities? If you take metric gravity, this is the part which is.
Excuse me,
Yes.
me, Misha. Are you changing the slide? We see only the first page up to now.
I see. I was turning the slides, but evidently something didn't work. Let's see. You see the first slide now?
Yes, I can see the first slide.
Yeah, let's see. Okay, but now you don't see. Just 1 second. Do you see?
Page 3.
Okay. So you see, so now the second slide, I hope.
Yes, I see the second slide.
Okay, so here I was just giving references to the papers which I'm going to describe. And here is my outline. You see outline now?
Yes, I can see.
Okay, and so now I'm on this slide where I'm reminding you different formulations of gravity. Okay, so the metric gravity, this is the gravity which is most well known. So everybody knows how it is constructed. So what you do, you define a Riemann curvature tensor through connection like this. Now, in metric gravity, the Christoffel symbol connection is symmetric with respect to lower indices. And then from the fact that covariant derivative of the metric tensor is equal to 0, you can express gamma in terms of the metric. In this way, you express Riemann tensor in terms of the metric, and you express curvature tensor just in front via the metric. And then you can write the lowest order action without cosmological constant. I'm not going to talk about cosmological constant here. And here is the Einstein-Hilbert action. Now you make a variation of this action with respect to the metric, and that gives you the vacuum Einstein equations. Okay, so this is what we can call the metric gravity. So now, what is the Palatini gravity? Okay, the curvature tensor is expressed via connection exactly in the same way. Okay, so this is the universal features of all gravities I'm going to talk here about. The connection gamma is still a symmetric quantity with respect to lower indices. Then what you do, you write exactly the same action as in the metric gravity, but now you consider the connection gamma and the metric as independent variables. And to find the equation of motion, you make a variation both with respect to gamma and with respect to the metric. So if you find variation with respect to gamma, that gives you equation of motion, which tells that covariant derivative of the metric is equal to 0. So that reproduces you the relationship between connection and the metric. The variation with respect to G mu gives vacuum Einstein equations, and at the end of the day you get a theory which is exactly equivalent to the metric gravity. So the only difference is the different set of independent variables you started with, but at the end of the day this is all exactly the same. Okay, finally, Einstein-Cartan gravity. So this is the theory which was introduced by Einstein-Cartan, and lately in the works of Utiyama and Kibble, the same theory appeared if you gauge the Poincare group. Okay, I will talk also about that a little bit later, but now at the level of similar formulas, it's this theory is derived in the following way. You have again the Riemann curvature tensor, which is expressed via connection exactly in the same way as previously. Now, the symmetry of connection with respect to two lower indices is not assumed. So that means that theory has yet another geometric structure which is called the torsion tensor, and which is the antisymmetric part of the connection. Okay, so now you write the lowest order action, and there are several new terms which appear here. Okay, so the first term is exactly the same as in metric gravity. Then there is yet another term which is called Hall's term, which is written here. Okay, so normally in the metric gravity, this combination, this connection of antisymmetric tensor with R would give you a 0, but now this is not the case anymore because gamma are not necessarily symmetric with respect to lower indexes, so this is a legitimate term. And then there is also yet another term, which here is just a full derivative. It's called the Nieh-Yan topological invariant, and this guy is expressed through the torsion tensor. Okay. There are several new parameters appearing here. So there is parameter gamma. So MP is the Planck scale here. So this is an arbitrary number which has a name, Barberi-Emirzi parameter. So this mass scale here is also an arbitrary number. Okay. So now what you do, you take this theory. Your dynamical variables are again connection and the metric. You find variation with respect to gamma. You write all this variation, and you find that this theory is again equivalent to the metric gravity. It happens that the equation of motion imply that the torsion tensor is equal to 0, and then everything what we had before is reproduced. So this mass square which stands here in front of the Nieh-Yan invariant doesn't play any role. Well, this is obvious because this is full derivative. What is less obvious is why this new Hall's term is relevant, but it happened to be irrelevant. Okay, so again, this theory of pure gravity is exactly the same as the metric theory. However, the situation changes if a scalar field is introduced. Okay, so it can be, well, this scalar field can have an arbitrary nature, but what I'm going to do in this talk, I will be assuming always that this is the Higgs field in the standard model, and since gauge effects like SU2 will not be relevant for us, I will consider this scalar field in the unitary gauge. Okay, so the scalar action for this field is just written here. It's just a normal kinetic term, potential. This is the Higgs potential. And now we can add to that the gravity part. Okay, and the gravity part, since we have a scalar field at hand, then in addition to the previous terms, in which we had the coupling of, say, scalar curvature coming with the m Planck square, we are allowed, and actually should, or must, add different non-minimal terms in which Higgs field square is added to the Planck scale with a priori arbitrary coefficients. Okay, so here is this term. It would be the same as in metric gravity. Okay, so we have m Planck square plus psi h square times r. Then the Hall's term, which was contained in this antisymmetric contraction of the Riemann tensor, also comes with coefficient m Planck square plus some non-minimal coupling, psi gamma, I will call it, times h square, and finally Nieh-Yan invariant, which was irrelevant for the pure gravity case, becomes relevant because this is total derivative, but it's multiplied by dynamical field h square. Okay, so if so we get a theory which, in addition to the Planck scale in the gravity sector, contains three other parameters, three non-minimal couplings, kind of coupling psi, which we are all familiar with, but then there are two other non-minimal couplings in the Holst term and Nieh-Yan invariant. Okay, so if we cross away two last lines, then we will get the Palatini action with non-minimal coupling. So that's also a theory which was considered in the past. So this theory is interesting, and it has the following properties. So in spite of the fact that we have all these three non-minimal couplings, still torsion field happens to be non-dynamical. So the torsion is not equal to 0, but it's expressed through other degrees of freedom. So that the number of degrees of freedom in this theory is exactly the same as in metric gravity. So that we have 2 degrees of freedom for graviton field and 1 degree of freedom for the scalar. So the fact that it has the same number of degrees of freedom allows to rewrite this theory entirely in the metric formalism. Okay, so what you do, you can construct the Lagrangian, which has exactly the same physical content, but in metric gravity, so that only the metric plays a role of dynamical variable. So there are several technical steps which should be done here. I'm not going to discuss them. This is pretty much straightforward. So the trick is to make a Weyl transformation of the metric and then produce several manipulation. So the result is that what you find out an equivalent metric action which has this form. So here you recognize the first term, which is the standard for the metric gravity, and then you find out the action for the scalar field, which is modified in comparison with the previous simple action. So there are different modifications to make. So first of all, the potential is divided by this conformal factor, 1 plus psi h square over m Planck square. Okay, and that's very interesting because then this potential is mathematically flat at large values of the Higgs field, and this is known to be a very good feature for inflation. Okay, and then there are several modifications of the kinetic term of the scalar field. Okay, so there is some factor which appears in front of derivative of the scalar field, which is again associated with the with this conformal factor, and then there are several additions which are all coming from this new terms, from the Holst term and from Nieh-Yan invariant. Okay, so what I will do, yeah, and we will see that these extra terms, in particular kinetic term, happen to be essential for non-perturbative generation of the Electroweak scale, and they're also important for description of inflation. Okay, so first I will discuss the Fermi scale. Okay, so we know that the question why the Fermi scale, which is about mass of the Higgs boson, about 100 GeV, so this scale is much smaller than the quantum gravity scale, 10 to the 19 GeV. So this is a celebrated hierarchy problem. And there are many proposals to deal with that. So these proposals include low energy supersymmetry, large extra dimensions, composite Higgs boson. So all these proposals were predicting particles at the Fermi scale. It was expected that these particles will be found there. However, none were discovered so far. And this, I believe, calls to rethinking of all this stuff. Okay, and so together with Andrei Shkerin, we came out with the following proposal. So there is just one fundamental scale in nature. This is M Planck, and the Electroweak scale is generated from it in some non-perturbative way. Okay, and if we talk about non-perturbative way, so there could be different non-perturbative effects, and the non-perturbative effect which we have in mind here is associated with the tunneling phenomena, which can be described by semi-classics. And so what I'm going to argue that this semi-classical solutions, instantons, well, here it will be a particular gravitational instanton, may be contributing to and producing a non-zero Electroweak scale. Okay. So this is actually a kind of natural idea. If you write the Higgs mass in this form, mh squared is equal to m Planck square exponential minus s. So if this number s is about 80, well, not a very large number, then you are getting the required hierarchy. And we know in nature quite a number of different realizations of oops. Oh, just 1 second. Yeah. So you see my slides now with alpha particle.
Yes, I can see the slide.
Yeah, slide 9. Okay, thank you very much. Okay, so there are several phenomena which we know very well, which may lead to such a big difference in scale. So one of them is the theory of alpha decay, in which we have a decay of heavy nuclear to another nuclear with emission of alpha particle. And here you would expect that the decay rate is very high, inverse MeV, but in fact it's much many orders of magnitude smaller, and this decay is suppressed by the Coulomb tunneling exponent. Yet another example, but there are many, is in molecular physics, when you can get a frequency of transition between two nearby levels exponentially suppressed in comparison with the energy of the level itself. Okay, so for this non-perturbative mechanism to work, of course, the theory should satisfy quite a number of different requirements. So first of all, if you talk about non-perturbative effects, then perturbatively, the Higgs mass must be equal to 0. Okay, if it's not equal to 0, then any non-perturbative contribution suppressed by the tunneling exponent will be smaller than the perturbative contribution. So we should have a theory in which, in all orders of perturbation theory, mass of the Higgs boson is equal to 0. Okay, then we should have an absence of super heavy particles coupled strongly to the Higgs, because in this case we will get perturbative contributions to the Higgs mass, which are pretty large. And finally, of course, the theory should possess non-trivial semi-classical configurations, which can lead to a non-zero value of the Higgs field, or to non-zero value of the Higgs mass. Okay, so let me discuss first the requirement that mass of the Higgs should be equal to 0 in all orders of perturbation field. Okay, so the question is whether we have a symmetry we can ensure this, and the answer is yes. Okay, so if the mass of the Higgs boson is put to 0 in the standard model, then the classical Lagrangian has a wider symmetry. It is scale and conformally invariant. And this symmetry, dilatations, or in the case of standard model, there is even a wider symmetry, which is a full conformal group. So what you do, you change the scale of coordinate, you change the scale of the field. Okay, and this symmetry forbids the mass of the Higgs boson. And if you take the theory which is classically scale invariant, then the Higgs mass can be predicted, and this was first explored by Coleman and Weinberg in this famous paper, Radiative Corrections as the Origin of Spontaneous Symmetry Breaking. Okay, so they said that scalar to vector mass ratio is computable as a power series in electric charge. Okay, and they found this relationship. So let me remind you how it goes. So you take the abelian Higgs model with the scalar self-coupling lambda, which is very small, of the order of g to the 4th, where g is the gauge coupling, and you put the Higgs mass equal to 0. Okay. So this theory is classically scale invariant, but there is conformal anomaly, and this conformal anomaly leads to dimensional transmutation. Okay, so we get a non-vanishing trace of energy momentum tensor, etc., etc. But the main point here is that if you look at the running of the Higgs mass, then the running of the Higgs mass is logarithmic, and moreover, renormalization group equation for the Higgs mass has a fixed point when mh is equal to 0, or to put it in other words, so this derivative of the Higgs mass is proportional to the Higgs mass itself, and therefore, if mh is equal to 0, then it's not run. So basically, you don't need a counter term for the Higgs mass. Okay, the important point, of course, is that any power-like divergent contributions to the Higgs mass are purely technical and are introduced by explicitly breaking the conformal invariance by regulators. Okay, in original Coleman-Weinberg paper, the normalization conditions were the derivative of potential at phi equal to 0 is equal to 0, and the fourth derivative, which gives us the physical self-coupling, is equal to lambda. Okay, so what you do then? You compute the Coleman-Weinberg effective potential, discover that U1 theory is in the Higgs phase, and then you read off the ratio between the Higgs boson mass and the vector boson mass, and this is the formula for the Coleman-Weinberg paper. Okay, so this idea, of course, it was very exciting, and it excited many people. Linde, Weinberg, okay, here is the partial list, to apply these ideas to the standard model. Okay. However, it happened that the idea doesn't work on the standard model. Okay. Originally, people thought that it may work. From here, an upper limit on the mass of the Higgs boson has been derived, few GeV, but this was all rejected by experiment. So the situation is the following, that if the top quark mass is smaller than some critical value, then the minimum of effective potential for the Higgs field is generated at very small values of the Higgs field, about 100 mega-electron-volt, due to chiral symmetry breaking in QCD. Now, if the top mass is greater than this critical value, then an extra minimum of the effective potential is generated at the Higgs values, which are greater than the Planck scale due to the top quark loops. Okay, so both situations are not acceptable from a phenomenological point of view, and therefore it doesn't work. Okay, and by the way, this critical Higgs mass is very close to what the critical top mass is very close to what is observed experimentally. Okay, so it's clear that this idea of radiative generation of electroweak symmetry breaking in the standard model fails. And if you want to stick to it, then some new ingredients are necessary. And indeed, there were many different theories which were constructed to implement the Coleman-Weinberg breaking of the electroweak theory with extra gauge bosons, extra fermions, extra scalars, etc., etc. However, all that is, I mean, all these modifications, they are missing a very essential point that in any realistic theory must contain gravity. Okay, and gravity comes with a dimensional full parameter, which is the Planck scale, which is much, much greater than the Higgs mass. And therefore, the gravity must be taken into account because it does introduce an explicit breaking of conformal symmetry, explicit breaking of scale invariance, which was assumed previously. Of course, throwing on the gravity completely, it does have a rationale. So if you take any mass-independent regularization, such as, for instance, dimensional regularization, then you find that there is no contribution to the Higgs mass coming from the gravity corrections. Okay, so all gravity corrections are inversely proportional to the Planck scale. And so in any regularization procedure, which is mass independent, such as dimensional regularization, the RG equation for the Higgs field still has this property that mass of the Higgs boson is equal to 0 is a fixed point. Okay, so but what is interesting is that gravity plus the standard model is an example of the theory where Higgs mass is equal to 0 in all orders of perturbation theory. Okay, and therefore this theory may serve as a playground for understanding of non-perturbative generation of the weak scale. Okay, so what I'm doing now, I'm taking our Einstein-Cartan gravity. I'm not going to take it in the most general case. Let's just take a theory without host and Nieh-Yan terms. So we are taking gravity in Palatini formulation, and I will comment on more generic situation later. And let's see whether in this theory any non-perturbative mechanism for generation of the weak scale can work. Okay, so this is again the Lagrangian simplest theory. Just a remark that the cutoff of the theory, the onset of perturbation theory breaking, is situated at m Planck divided by square root of psi. So at this energies, the processes, scattering of different particles cannot be already computed in perturbation theory. Okay, so what we want to do, we want to take this theory, and we want to compute the wave of the Higgs field, and everything in this theory is dynamical. Okay, the metric, the scalar field. Okay, I'm going to do this computation in Euclidean path integral. Okay, the Euclidean path integral may not be well defined due to the problem with conformal factor of the metric. I'm not going to argue in favor of that and just follow quite a number of papers which done the same by Hawking, Coleman, DeLucia, etc., etc. Okay, so we'll assume that the Euclidean construction makes sense. Okay, so if we compute this integral, then there are several domains for the field phi. There is domain in which field phi is small, okay, but then gravity is irrelevant, and no contribution to the wave of the Higgs field can come from perturbation theory. So this is just the normal perturbation theory. So the challenge is to see what happens at phi much larger than m Planck. Okay. So the theory for phi much larger than m Planck, it's like here, in which we neglect m Planck. And so this is the theory like this. And this theory is also very interesting. So in this theory, there is a scale invariance because there are no dimensional full parameters. And also in this theory, the Planck's scale is dynamical. Okay, so you see that the coefficient in front of that depends on the Higgs field. Okay, so we have to decide how to account for contribution with so large phi. And our conjecture is that this is better to be found in Einstein frame. Okay, because in this way we remove the dependence of the Planck scale on the Higgs field. Okay, so it's an easy to make a transformation to Einstein frame. So this is achieved by introducing, by making a conformal transformation which removes this factor and modifying the scalar field to account for this transformation. Okay, and so what you find is that the resulting action is the normal Einstein term, the normal kinetic term, the potential, okay, which is flat at values of phi. But what is important is that this transformation here introduces the source term in the path integral. Okay, so we are computing the average value of phi, and at large values of phi, we have here an exponential. And this exponential appears here in the action. Okay. So now, if you want to apply semi-classical methods, we should find out the minimum of the action. And now the minimum of the action, what we have in the exponential, not only contains the this action here, but it also contains a singular source term. Okay, and this means that the equations of motion are modified. Okay, and this is kind of a known phenomenon which appeared already in a number of circumstances. Okay, so the most trivial example is, of course, computation of this one-dimensional integral for large n. So if you use a saddle point, e minus x squared, for computation of this integral at large n, you will get the wrong result. So you have to include the part which coming from this x to the power n. The multi-particle production also leads to the similar modification of equations of motion. Yet another famous example is the proof of confinement of three-dimensional George Glesher model by Polyakov, where you have to include this part coming from Polyakov-Wilson loop into equation of motion. Okay, so what is coming now is kind of a straightforward realization of this idea. Okay, so you take the source term, you take the action, and then you find a solution for the scalar field and for the metric. Okay, so you can use O4 symmetric metric. You can find equations of motion. You can solve them, and indeed you find a new solution, a new singular instanton. So this instanton happens to be singular, and the singularity is coming from the source term, which is a delta function. So this is an unphysical situation. Singularity should be smoothed, and a way to smooth these singularities is to have this action with the addition of higher dimensional operators. Okay, so these higher dimensional operators, they should be there, and if you add these operators, okay, there could be many of them. So we have picked up an operator which doesn't introduce new degrees of freedom. It doesn't FOIL scale invariance when the scalar field is equal to large. So this operator, it includes higher derivative of the scalar field. You cannot also here this derivative to the fourth power, but then you may be in conflict with the positivity requirements. So this is a safe operator to add. And now you can study what happens with the Euclidean action in this theory. So can you find a solution which would give you an Euclidean action of the order of 80, which would reproduce for you the required hierarchy between the Higgs wave and the Planck scale. Okay, and this plot here, it shows when this is possible. So this axis is a logarithm of this non-minimal coupling psi, and this axis here is a constraint on this parameter delta, which we introduce here and which parameterizes this operator. Okay, so if you take a natural choice when delta is of the order of psi square, then this operator has the same UV cutoff as the original theory, m Planck divided by square root of psi. Then this line here tells you what the choice of psi and delta will give you a correct action. Okay, so it's gratifying to see that this ratio is of the order of 1, but what is also required is that this parameter xi should be sufficiently large, and so this domain here, it will be a constraint coming from inflation and from top quark mass, and these 2 points I will discuss somewhat later. Okay, so the message is that the hierarchy between the Planck scale and Fermi scale may be a natural phenomenon when the standard model is classically conformal, okay, and that we need in any event to have no perturbative correction to the Higgs mass, and this parameter xi, non-minimal coupling, is large. Okay, it's amazing that the requirement of successful inflation also leads us to the conclusion that this non-minimal coupling must be large. Okay, so I finished with the generation of the Fermi scale and coming to inflation. Okay, so if you take our action, which we already discussed, then this action generically leads to the Higgs inflation. So why so? Because the potential U divided by omega to the 4 is a flat at large values of the Higgs field. Okay, and we can look at different variants of the Higgs inflation. So metric Higgs inflation is realized at specific choice of parameters of these 3 non-minimal couplings. We can get Palatini theory, then we are getting Palatini Higgs inflation, and both theories are known to work. So this is a busy slide which shows what is the difference between metric and Palatini Higgs inflations. So all of them are parameterized by this action, which is written here, but which I rewrote here, just introducing some coefficient in front of canonical kinetic term for the Higgs field. Okay, so the main difference between these 2 incarnations is that UV cutoff for the metric theory is in Planck of xi, and UV cutoff for the Palatini theory is parametrically larger. So if xi is large, here we have square root of xi. So both theories leading to the same prediction for the scalar perturbations. So it's 1 minus 2 over n, where n is the number of e-folding, but they are leading to very different predictions for the gravitational waves. So in both cases, the gravitational waves are small, okay, for the Higgs inflation. In the metric formalism, it's of the order of 10 to the minus 3, and Palatini formulation is about 10 to the minus 11. Okay, and so this analysis, I show again this picture. So this axis, so the bound on parameter xi comes from inflation. Okay, so it's basically Kobe normalization, which fixes xi for you in the case of Palatini equation, and this happens to be that xi should be greater than 10 to the 6. There is yet another limit coming from top quark mass, and which appears in the following way. The scalar self-coupling runs, so it should be positive in inflationary domain, and the requirements that it is positive also limits parameter psi. Okay, so you take the experimental values for the top quark mass, you account for uncertainties there, and you transfer this knowledge about top quark mass on parameter psi. Okay, and so it happens that this psi is bounded from above, it's bounded from below, and also in this domain, everything works fine. Okay, so, but in addition of these two types of inflation, the metric and Palatini, we get the whole area of different possibilities, because there are three non-minimal couplings, and by varying this minimal couplings, you can go from one case to another, and you can find out other types of inflation. Okay, so there are several possibilities. Some of them can be studied analytically. Some of them require some numerical simulations. So, for instance, one can say, okay, suppose that the host term is equal to 0. Or then one can say that the Nieh-Yan term is equal to 0, and then you can see what is happening in these cases. Or you can even go through a more ambitious program in which you take these parameters as they are and do a Monte Carlo search of inflationary parameters with the use of arbitrary choice of all these non-minimal coupling constants. So I will show you a few plots which demonstrate how this transition between different types of inflation is happening. Okay, so this is what we call the Nieh-Yan Higgs inflation. You choose the parameters in such a way that the host term is equal to 0. And then you consider what happens if you vary the parameters. And then you look at the inflationary predictions. So what this picture shows. So horizontal axis is always the value of non-minimal coupling psi, okay? And the vertical axis is the value of yet another non-minimal coupling which appears in front of Nieh-Yan term, okay? And this is the line which correspond to the fixing of co-normalization for the Higgs inflation. And the color code here gives us in this case, this is for NS, and in this figure, this is for R, okay? And then there are different parts of this curve. So if you look at the left plot, for instance, there is this vertical part which corresponds to the Palatini inflation. Okay, so here all NS, they're all in the region of 0.96. However, you see that this guy is very, very blue, so it corresponds to a very, very small gravity to scalar ratio. Okay, so R is very, very small in this part. So this is a Palatini case. Then everything is changing, and we are coming to the metric Higgs inflation, in which the amplitude of gravitational waves is larger, but still the scalar tilt is the same. So what is very interesting is that if we move in this direction, so decreasing psi, then we are entering into a regime in which the amplitude of gravitational waves increases. Okay, so what was believed to be a very specific feature of Higgs inflation, the suppression of gravitational waves, is associated with metric and Palatini Higgs inflation. And in more generic case, this is not true, and the amplitude of gravitational waves can be pretty large. Okay, I don't think I will go through other cases. They can be found in our paper. I will just flash you the different distributions which appear in more elaborated analysis, which accounts for all possible couplings. So you can make this three-dimensional plots which show you what kind of NS and R you will get in this with this or that choice of parameters. And I will just conclude this part of the talk by saying that inflation is a generic phenomena which occurs basically in almost all parts of the parameter space of this theory. The largest parts of the parameter space reproduce the predictions of either metric or Palatini Higgs inflation. The spectral index, NS, happens to be mostly independent on the choice of couplings and lies very close to 1 minus 2 over n, where n is the number of e-foldings. The new point is that the scalar to tensor ratio, tensor to scalar ratio, can be pretty large, which gives hopes that this can be detected in the near future. And finally, is that there is a domain of parameters of non-minimal couplings where the mechanism of the generation of the Fermi scale from the Planck's scale seem to work. So it's this domain in which nu and 1 non-minimal coupling is sufficiently small. Okay, so I have to conclude. So the part which is associated with dark matter production will be very short, but in fact it's more or less straightforward. Okay, there is yet another feature of Einstein-Cartan gravity which I haven't discussed yet. So I discussed just the bosonic part of it, but there are fermions in the standard model. Okay, and it happens that if there are fermions in the theory, this results in a new interaction between fermions. Again, this is a four-fermion interaction. So how this is done technically? Okay, the better language for discussing fermions in Einstein-Cartan gravity is to deal not with the metric and Christoffel symbol gamma, but with tetrad frame field. Okay, it's associated with translation, and spin connection, which is nothing but the gauge fields of the local Lorentz group. Okay, so what you do, you write a more general, most general term for the fermionic action. It happened to contain some new parameters again. So to some extent, these parameters are similar to this Holst term, new Holst term, and new Nieh-Yan invariant. And here there are also new parameters which appear in the action. You start from that, you solve for torsion, and what you find at the end of the day, that the theory contains a new four-fermion interaction. Okay, the strength of this four-fermion interaction depends on this so-called non-minimal couplings, alpha and beta. It is suppressed by the Planck scale, and it contains axial times axial current, axial times vector current, and vector current square. And all fermions participate there, okay? All fermions which we have in the standard model, plus extra fermions if they exist, okay? A natural candidate for dark matter particle is a singlet fermion, and so this singlet fermion is present in this four-fermion interaction. And since it's present in this four-fermion interaction, it can be produced in interaction of ordinary particles. So if you take any particle X of the standard model, they can annihilate and they can produce this new fermion. So you can do a computation. Again, this is a pretty straightforward computation, and compute the abundance of these fermions. Okay? And here is the formula for this abundance. It contains a factor which is corresponds to the mass of this fermion. It contains a factor which is expressed through these non-minimal couplings, and it also contains a factor which is associated with the maximal temperature of the universe after reheating, after inflation. Okay, the higher is this temperature, the more fermions are produced. Okay. There could be two natural choices of non-minimal couplings. Okay, well, natural, quote unquote. Okay, we don't know what natural is, but okay, we can take the theory in which these couplings are completely absent. So alpha and beta are equal to 0. Still, these fermions are produced, and in order to get the right abundance, the mass of this fermion should be of the order of 10 to the 8 GeV. There is yet another choice, which is also natural, in which this new parameters alpha and beta is chosen in such a way that the cutoff, UV cutoff associated with this four-fermion interaction has the same order of magnitude as the cutoff in the scalar sector, which is M Planck over Xi. Okay, and then you find out that the correct dark matter abundance is obtained for keV scale fermion. Okay, so the whole spectrum of masses from keV to 10 to the 8 GeV can be covered by this mechanism. Okay, I overpassed my time, but I will just show you my last slide. This is application to Nieh-MSM. So Nieh-MSM is a theory in which Electroweak nothing changed besides adding 3 right-handed neutrinos. So this theory can give Electroweak symmetry breaking, inflation. It can explain baryon asymmetry of the universe. And one of these particles and one in keV range can play a role of dark matter. And so people normally, well, including myself, were telling that there is an upper limit on the strength of interaction of this particle to everything else. This is this mixing angle, but there is also a lower limit, okay? Because if this coupling is very small, then no particles of this type can be produced. And so this mechanism of fermion interaction allows to produce this particle, and no constraints of previous type are applicable to that. So that's, I find interesting. And so I'm coming to my conclusions that Einstein-Cartan gravity is an interesting theory with the following properties. It has the same number of degrees of freedom as metric gravity. It may lead to an explanation why the Fermi scale is much smaller than the Planck scale. The Higgs inflation is a natural consequence of EC gravity with universal prediction for the scalar index and with gravitational to scale ratio, which can be as large as the previous experimental limits. And it also leads to a new universal mechanism for fermion dark matter production. Thank you very much for your attention.
Thank you very much. So question. So if you have a question, then switch on your mic and camera and ask. So question.
May I ask a question? First, I have a question about the reheating. I'm curious about what makes a difference between the metric formulation and the Palatini formulation in the reheating. So you have shown the table, and yeah, it seems the different values show up in the reheating. So both are caused by the Higgs decay, right?
Yeah. Okay, so in both cases, the reheating is instantaneous. Okay, instantaneous means that the Higgs field, well, potentially the Higgs field at the end of inflation may start oscillating like that. Okay, but in fact it doesn't, and it decays into the stuff on the standard model. So for the case of the Higgs inflation, the main channel for reheating is actually a production of longitudinal W and Z bosons. Okay, this goes very fast. Whereas for Palatini case, the mechanism of reheating happens to be somewhat different. So in the Palatini case, the potential is flat, and so the Higgs field travels to the plateau. And in this plateau, what happens is that the system is unstable, and simply because the curvature of the potential m square, second derivative of potential, happens to be negative. Okay, and so that gives you another mechanism of reheating. The difference between these two numbers is coming because of the following. So since the reheating is instantaneous, to find the temperature of reheating, you basically use the energy of the Higgs field at the end of inflation and distribute it over particles in the standard model. Okay, and this reheating temperature contains this parameter square root of psi. Okay, so it depends on this way. The larger the psi, the smaller is the energy of inflation. Okay, and in the Palatini case, the choice of psi is much larger than for the Higgs inflation, and that explains the difference between this temperature. So for the Palatini case, this plateau for the Higgs field is much lower than
I see. Thank you. And also, I have some questions on the dark matter production. I guess there's also a graviton exchange contribution, but
yes.
Does it is it negligible in this case?
Yeah. Okay, that's a very good question.
Yeah.
Of course, people discussed long ago, okay, the gravitational production of dark matter, which happens in the following way. So once you have whatever particle you have, you consider this particle in the time-dependent metric, and the fact that the metric is time-dependent leads to production of this particle. Okay. this mechanism, of course, also works, but it happened to be only essential for masses greater than 10 to the 9 GeV particles. So there is some complementarity. This pure gravitational production is operating for very heavy particles greater than 10 to the 9. So, and this four-fermion interaction is operating for smaller mass particles.
I see. I see. Okay. Yeah. Thank you.
You're welcome.
Okay, any other question?
I have a question for your mechanism to generate the fermion scale from the Planck scale. So when you have the non-linear coupling, you introduce a term in path integral. So why the Einstein-Cartan gravity is essential for this mechanism?
Okay.
So do we get the same term in the matrix theorem?
Yeah, that's a very good question. This and this happens because of the following reason. So this is an equation of motion for the scalar field, for the instanton, okay? And it contains this parameter square root of psi, okay? And these equations were written for the case of Palatini gravity, okay? Now, the action for the instanton happens to be proportional to this square root of psi, okay? And again, the fact that psi is very large allowed us to have sufficiently large action. So if you will do exactly the same computation for the Einstein gravity, or just metric gravity, the source term here in front of this delta function will have a different dependence of psi. And basically, independently on the value of psi, the source term happens to be too small, and the action happens to be too small. Okay, and yeah, maybe I will show you this this part. Yeah. Okay, so you see that the strength of this source term is now coming from this part of kinetical term and that part of kinetical term. And just for the metric case, it happens to be small. Okay, so you just get that the Higgs wave is of the order of Planck scale. Okay, so that the Higgs wave is brought to the very, very high values. Okay.
I see. Thank you.
Okay, any other question or comment?
Yes, I have one question. So you worked in the Einstein frame, and do you get the similar result in the Jordan frame too?
Yeah. So I mean, the choice of frames is basically the choice of coordinate description. Now, all the results are the same on all frames. The advantage for the Einstein frame is the following. Okay, so if you take inflation, most of results derived in the literature are derived for the Einstein frame, and so when you convert everything to Einstein frame, you can use other people results.
Mm-hmm. Yeah, I was curious because you said it's a kind of conjecture. Your slide.
Yes. Yes. For generation of yes, for generation of the Fermi scale, this is indeed an important conjecture. So when you compute an integral, path integral, or whatever integral, if you want to compute, or if you compute this integral exactly, then of course you can do that in whatever variables, right? It doesn't matter if this is an exact computation, okay? Now, if you do an approximate computation of the integral, the choice of the saddle point matters. So, for instance, take this one-dimensional integral, right? You can say, okay, I will compute this integral approximately, and I will use the saddle point, which is just x squared. Then the saddle point will be x equal to 0. And then you compute this integral and you find the answer, which is not correct if n is large. Okay. Now you can say the following. Okay, since n is large, I better exponentiate this x to the power n. And so my action will be x squared plus n log x. And now I find another saddle point, insert it back, and then I will get a correct result. So this is exactly the similar type of procedure. So we look at that, then we make a transformation to variables which we believe is more appropriate for computation of this. Okay, and then the check to make would be the following. You take one saddle point, and then you compute the determinant of fluctuation near this saddle point. Then you take another saddle point, and again, you make a computation of determinant near this saddle point. And that should tell you which saddle point to take, okay? And so this part is at the level of conjecture because we didn't compute this determinant around this solution, okay? That happens to be a very challenging problem which we plan to attack, but we haven't done so.
Okay. Okay, thank you very much.
Okay, question or comment? Okay, if not, let's then speak again. Okay, thank you very much, Professor.
Okay, thank
you very much.
Your question.
Bye-bye.